Welcome to lesson 22, Simple Harmonic Motion. Today we look at the physics behind anything that oscillates. Here's the plan for today. Start with the pendulum, like in a grandfather clock. It swings out, comes back through the middle, swings out the other side and returns. That middle point, where it would hang at rest, is the equilibrium position, and everything is measured from there. Sketch its displacement against time and you get a sinusoid, a smooth wave. And notice frequency and period are the same idea as always, linked by F equals 1 over t. Now, velocity is the rate of change of displacement, and acceleration is the rate of change of velocity. So each graph is the derivative of the one above it, and each ends up a quarter of a cycle ahead. Let's read them physically. At the extremes, maximum displacement, the object is momentarily stationary, so velocity is 0. But that's where it's being pulled back the hardest, so acceleration is at its maximum. At the centre, it's moving fastest, maximum velocity, but there's no restoring force there, so acceleration is 0. Velocity peaks where acceleration is 0, and vice versa. Here's the definition, and it's the one thing to memorise from this lesson. Acceleration equals minus omega squared x. In words, the acceleration is proportional to the negative displacement, and it points back towards the equilibrium position. That minus sign is doing all of the work. It's what makes it oscillate rather than fly away. The further you pull it out, the harder it's pulled back. The solution to this equation is x equals a cos omega t, where a is the amplitude and omega is set by the physical system. It can depend on the mass, spring constant, or length. If you can prove that a system obeys a equals minus omega squared x, then you have proved it performs simple harmonic motion. That's a standard exam demand. So what are some examples of systems that actually do this? First, a mass on a spring. Hooke's law tells us that the restoring force is proportional to the extension, F equals kx, which is exactly the proportionality that simple harmonic motion requires. So a spring oscillates harmonically, guaranteed. Its period is 2 pi square root of m over k. Think about what that depends on, mass and spring constant. A heavier mass swings more slowly, a stiffer spring swings faster. And notice what's absent, the amplitude. Pull it out further and it still takes the same time. That surprises people, but it's a hallmark of simple harmonic motion. The pendulum is subtler. Its restoring force is proportional to sine theta, not to theta itself, so strictly it isn't simple harmonic. But for small angles, sine theta is very nearly equal to theta, which effectively straightens that sine curve into a straight line. Under the small angle approximation, we get A equals minus g over L times x, which is our simple harmonic motion equation. So the period is 2 pi square root of L over g. It depends only on the length and the gravitational field strength, not on the mass of the bob, and not on the amplitude. Change the bob for a heavy one and the period is identical. Both of these examples are really important for exams. Finally, energy. And it swaps back and forth, just like the pendulum in lesson 14. At the extremes, the object is momentarily still, so all the energy is potential. At the centre, it's moving fastest, so all the energy is kinetic. Everywhere in between it's a mixture, but the total stays constant, assuming no friction. And one result to state, the maximum speed, which occurs at the centre, is omega times the amplitude. V max equals omega A. You don't need to derive it, but it's one that you need to know. That's the end of the video. Thanks for watching, and check out my tutoring page below.